Good evening and welcome to this evening's session. My name is Donna Hearn and I am honored to be the chair of the Division of Organic Chemistry. And I'm particularly honored to chair this evening's session where we give the award to the Roger Adams awardee this evening, and that's Professor Larry Overman. The Roger Adams Award in Organic Chemistry basically is really the highest honor for the Division of Organic Chemistry. And I get to do a lot of things as the chair of the Organic Division, and this is one of my favorite things I get to do. This award is to recognize and encourage outstanding contributions to research in organic chemistry defined in the broadest sense. And when you read this, what this means is that in the broadest sense means you could give it to someone who is good in research, who's good in service, and who's good in education. And what's great about tonight's recipient is he's good in research and in education and in service. And so I'm particularly proud tonight that our recipient is Professor Larry Overman. So if you read a little bit about Roger Adams, all of us know about the Adams catalyst, but I'm really struck by how what he did in the early 1900s really resonates with what we're doing today. So he was very interested in pharmaceuticals. He actually isolated some of the constituents of marijuana, very relevant to what we're doing today. He was also interested in restricted rotation, Scott Miller. So really things was as interesting then as they are today. He also had a significant contribution to how we educate graduate students. And he played very important roles in establishing two really important journals that we still talk about today and we're still involved in, and Larry's very involved in, Organic Reactions and Organic Syntheses. And those journals, as well as the Division of Organic Chemistry, are really important to supporting this award. So finally, to get to the most important reason we're here today, talk about Larry. Larry was an undergraduate at Earlham College. He received his PhD at Wisconsin with Harold Whitlock, and then did a postdoctoral at Columbia University with Ronald Breslow. He joined the faculty at UC Irvine in 1971, where he's now the Distinguished Professor of Chemistry. I think it's really safe to say if you think about UC Irvine, you think about Professor Overman. He's made numerous contributions. He's a member of many committees. I'll just name a few. He's a member of the National Academy of Sciences. He's held numerous leadership positions at Organic Reactions and Organic Syntheses, and he's been an executive committee member of the Division of Organic Chemistry. He's made significant research contributions. He has over 350 research peer-reviewed publications involving synthetic methods and total synthesis. We all know about the Overman rearrangement. We heard about Jeff Bodie trying to understand the azocope-manic reaction today. But so it's true, right? So you're trying to understand this reaction, but what I would say is that now whenever you look at a pyrrolidine, like how can you not think about that reaction? So that's how fundamental now that reaction is to what we think about. His total syntheses now are classics, right? So we talk about the morphine synthesis, the strychnine synthesis, and one of my favorites, the pumiliotoxin. You know, as a graduate student, all these things were coming out in the literature, and I just remember reading those coming out of Larry's laboratory, thinking, wow, because we never worked on nitrogens, and so who yesterday talked about the more nitrogens in your molecules, the scarier it was. So it was impressive. This is a great honor for me to be able to present this to Larry, and it's really hard to say things about Larry that haven't already been said. People talk about what a great mentor he is, how he contributes to our society and our profession. And so what I decided to do is I'm not going to find anything new, but Dave McMillan, right, so he has a number of people who we've all heard about and have made amazing careers already. But Dave McMillan, if you look on the website, there's a great video, a tribute to Larry, and Dave McMillan said things that I think are just perfect about Larry. He said, Larry cares about purity of science, purity of thought, and he's an upstanding human being. So I am very proud to present the 2015 Roger Adams Awardee, Larry E. Overman, for his prowess and ingenuity as a superb molecular architect in the design and synthesis of complex natural products of plant and marine origin.
very, very nice. This is the real one, I think. Yeah.
This is the real. This is the gold one.
Okay. Huh?
We'll let it fall out. So as a chair, I get certain perks, and here's one.
Even without a stick. Oh,
Yeah.
wonderful.
Wait, one more.
Oh, I have to get some of these.
Here we go, ready?
Okay, oh, perfect.
Okay.
Hey, Don. Thanks, Mark. Well, Donna, that was delightful. It's of course a great honor to receive this award. Roger Adams is the one that started organic reactions and organic syntheses, and as Donna mentioned, that's something I've been involved with, and coming up from the Midwest and knowing his impact and really, I think, pioneering one of the great institutions for chemistry in the Midwest, the University of Illinois. That was Roger Adams. And when I combine that with the people that previously have won this award, in fact, many of my my heroes in chemistry, and more recently, a number of my friends and people that gave me enormous support in my career, I feel particularly honored. So in that regard, I want to thank, of course, Organic Reactions and Organic Syntheses and Wiley and the Organic Division for supporting the award. Don, of course, for everything you do in the Organic Division, and Marissa, who's still hanging in there after a pretty busy week. I have some impression of how much is involved in organizing this meeting, so I really appreciate everything you've done. Okay, so what I thought I would do today is talk about a topic that I've really been involved with my whole career, and on and off, and quite intensively in the last half dozen years. And that is a problem that, as I've tried to point out, I think we've made enormous progress in the last 50 years since I've been doing chemistry, particularly in the last 10 years. But it's still a challenging problem, and that's forming quaternary carbon centers. When such structures exist in molecules, that is a particular focus of attention. Now, one way so here's what we're talking about. Here's the quaternary carbon. Quaternary carbon, of course, has only carbons as ligands, and the issues, I think, are fairly obvious, fairly well known, but I'll go over them. Steric congestion. Obviously, to form a quaternary carbon, you have to form carbon-carbon bonds. That's all there are. And except in very unusual situations, you can invert a quaternary carbon, so you got to get it right the first time. And the challenge and the progress that our community has made in this has been reviewed a number of times. We recently have a review I'll mention a little later, looking at one aspect of this. Well, I think one indication of the difficulty in synthesis of quaternary carbons is that if you look at the top 100, or a few years ago I looked at the top 200 pharmaceuticals, I think there were none of them that were made that had quaternary carbons where the quaternary carbon was made by synthesis. So here I show some of the winners in this time period, this 1 year time period in US sales. And then the top compounds that have quaternary carbons are similar to all the others that I know of that are top sales in the world. And they're molecules that are natural product derived, such as Avatar discus, which is obviously derived from a steroid precursor, and then Oxycontin, which is obviously derived from opium alkaloids. Well, what I decided to do in the talk is take the liberty. I guess this is one of the occasions you can spend a little bit of time talking about history, what brought me to this point. So I thought I would just, in the first part, pretty quickly go through how I got involved in this, how different times that we've dealt with this issue. And I thought it would also give the students in the audience a little idea of how in the last 50 years that I've been involved in the chemistry, how the problems we address as synthetic organic chemists have changed. So as the first slide shows, my first publication, the first real problem I ever solved in chemistry was dealing with making quaternary carbons, where my thesis problem was to look at the mechanism of the backbone rearrangement stage of steroid biosynthesis, and you can imagine we were going to look at whether you see positive charge delocalized in the basylic carbon by a Hammett study. But prior to doing that, I had to synthesize this. And the time I was a graduate student, this was not trivial in the mid-60s. Luckily, in fact, Barry Trost, a former winner of the Adams Award, taught me synthetic organic chemistry. I came from the small liberal arts college, didn't know a lot of chemistry when I arrived in graduate school. I was in the first course that Barry taught, and one of the things he described, which he was involved in his PhD thesis with Herb House, was dealing with, at that time, the issue not of how you make a single enantiomer or something, but how you even control position of alkylation of a ketone was very much under study, and people like Gilbert Stork were really pioneering in this area. But one of the things that Trost had developed during his PhD was to do a thermodynamic enol acetylation of a ketone to give you an enol acetate. I found that an enol benzoate was a better precursor. And then if you reacted that with an alkyl lithium, you could get a thermodynamic enolate. So obviously the second methyl group in this tricyclic system we're going to put together is going to put together an alkylation. But if you carefully make that enolate and you methylate it, you get a disaster. You get a mixture of what you want, which is a methyl group here, and you get a mixture of unmethylated di, tri, and monomethylated. So obviously, not surprisingly, the alkylation at this angular position to install the quaternary center was so slow that ketone enolate equilibration led to scrambling. Well, my PhD advisor at that time, very smart fellow, Howard Whitlock, suggested the following solution, which led to, I think, certainly one of the most exothermic Simmons-Smith reactions ever conducted, which was to take this enolate and preform Simmons-Smith reagent and add it to the enolate. Pretty exciting reaction, but it works quite well. If you worked it up the way I worked it up, there was a little iodine in the solution, and that led to a ring opening and led to a mixture of, it led to successful regioselective introduction to the methyl group as a mixture of stereoisomers. Now, this strategy for angular alkylation was later improved a lot. I think Konya was the first one that, rather than doing the enolate, trapped it with the silyl halide and then used cyclopropionate, that enoxysilane, and you can isolate the cyclopropanols. There's a lot of chemistry that was developed from this. Well, in my own academic career, as was mentioned earlier, we really got started looking at a number of molecular rearrangements. And after inventing the Isokop-Monish reaction, so I'll turn to the next slide, became interested in this class of classical natural products that all have this unit. They have a cis hydroindole with an aryl group at the angular position, and that's really the fundamental challenge in making these molecules. And I think this was really before catalytic asymmetric synthesis had much of a foothold at all. And the way this problem was addressed in my lab and other labs contemporaneously at that time was by a diastereoselective reaction. So as mentioned, I think earlier today, this crazy reaction, I think it's not so, as Donna pointed out, it's not so hard to think about using it. It makes a 3-acyl prolidine. And if you imagine, instead of an aldehyde here having 3 carbons that join from here to here, you can imagine an acyl indole. So that's what was done here. The strategy here was translating the critical stereocenter turns out to be the allylic alcohol. So we're transferring the stereochemistry of an alcohol to carbon. And this study material with silver nitrate, you get the aminimide, this design cascade, 3,3 sigma tropic rearrangement, Monash cyclization then leads in high yield to this product. So the older members of the audience might recognize, well, why the hell is this here? Well, this was here at that time because there weren't any catalytic asymmetric ways to make amino alcohols. So we used alpha-methylbenzylamine really to build this and set that center, and it's that center that dictates that. Well, of the reactions that have been developed in my lab, the isocote-Monash reaction is certainly the most robust. We've used it in a lot of syntheses and drawn back to it occasionally, and every time we set up to use it, it always works. So I can never say that for anything else we've probably done. So here's the key reaction. There's the acylproline here, part of this tricyclic ring system that's part of the 7 rings of strychnine. Here's the rearrangement. And one reason I include this is that the 33rd NOS at Bozeman, I think this was the second one that I had spoken at, the third that I had attended. Just a few weeks before that, we finished the synthesis, the first enantioselective synthesis of strychnine, and I still readily remember being able to talk about that at the 33rd NOS. Okay, it was about this time that the azocote-Monash reactions is leading us into a lot of different areas, and if you look at this enamide and you imagine that came from a ketone, you can again see a 3-acylproline, so you might imagine how we got to this position. And we got to this position in the context of making a molecule that was quite the rage for a long time, completely worthless molecule, but one that really spurred, I think, a lot of interesting chemistry. And certainly one of its biggest challenges is setting this spiral quaternary center, which is 1,3 related to another quaternary carbon, and you're in a chair cyclohexane that's rigidly held, so there's a lot of steric hindrance there. So we were looking at a number of ways of doing this, and one that we looked at was in fact a hex cyclization. And it worked remarkably well. I think the ratio here was something like 4 to 1. The major isomer was the one that we wanted. And this was a time in organometallic chemistry that cross-coupling reactions, such as the Heck reaction, were certainly being developed. Heck had done, pioneered gorgeously in this area, and then, rightfully shared the Nobel Prize for his contributions. But it was a reaction that hadn't, I think, really been employed in very complex contexts. And I was really struck with how well it worked here, and particularly struck when you go through the mechanism, realize that at the penultimate precursor, the final product, is some intermediate of this type. Now, undoubtedly, the six-membered ring flips into a twist conformation, but irrespective, there's enormous steric hindrance brought about by, in the major stereoisomer, having the palladium with its ligand field on the inside of this cis to the 2-carbon bridge in this bridge tricyclic system. So it struck us, if this was a reaction that would succeed in this context, it must have real potentially general utility in forming quaternary centers. So we examined that at a time in my lab in some detail. I show here some of the early syntheses completed in my lab using the intramolecular Heck reaction. And a key step, the red lines show the bond that's formed, and at least in the first of this talk, these circles indicate the quaternary centers. And I think even today, the intramolecular Heck reaction is certainly among the most reliable of our ring-forming reactions. 13 years ago, there were nearly 2,000 examples when J.T. Link surveyed this in detail in organic reactions. And I recently did a study myself and saw that this reaction has now been used in 140, really is a key step, in 140 natural product total syntheses, all since the first one was completed in 1999. Well, importantly in my career, this led us to trying to render this reaction enantioselectively, and we did that at the same time that Masako Shibasaki did. And in 1989, we reported the first examples of the catalytic enantioselective Heck reaction, which I think was the first reaction of any general utility, CC bond-forming reaction, any catalytic enantioselective CC bond-forming reaction. So I show here some of the molecules made with that early on. Our focus was always in using this to form quaternary carbons. I think you saw some of these molecules in Mohamed Movasaki's beautiful lecture of what he's done to really pioneer making these in a very efficient manner. So this really got us involved in asymmetric catalysis. And one thing that I had the privilege of doing was really reviewing in the last, just about a year ago, the state of the art in forming quaternary centers by asymmetric catalysis. And I was asked to do that by Nature because 10 years ago, we had written a review in PNAS about catalytic and enantioselective construction of quaternary carbons, and describing what a challenge this is. And I was struck if I just look at a few quotes from these two different papers. 10 years ago, I concluded that there are only 4 transformations: Diels-Alder reactions, reactions of chiral metal intermediates with carbon nucleophiles, intramolecular Heck reactions, and reactions of chiral carbon nucleophiles with electrophiles that were well documented to be useful. Now, in this day and age, in 10 years, the progress is really dumbfounding. And this was my conclusion 6 or 9 months ago. The methods now available for fashioning quaternary centers enantioselectively remove much of the previous barrier to incorporating such functionality in organic molecules for use in medicine, agriculture, and other areas. So in Nature review, you're limited to 100 citations, so we could only talk about 90 or 95 different contributions in this review. There were way over 200. So in this decade, the ability to form quaternary centers in catalytic and enantioselective fashion has just mushroomed, and it's, I think, a remarkable testament to the community. We saw some of the people we've already seen in this symposium, people that have contributed to that growth in this time period. Okay, that's what I wanted to say about history. I want to turn now to the major topic of my talk, and that is a program in our lab that is really founded on, really stimulated, inspired by this class of natural products, the so-called rearranged spongian diterpene lactones. So these are marine natural products isolated from a number of different sources. And they're, to my way of thinking, one of the most dissident families of terpenoid structures. They have your sort of standard terpene that I've shown in black here: decalins, hydroazolines, different things, typically non-oxidized is one exception here, Shaman K. But then linked to it is a remarkably highly oxidized 6-carbon unit that in most of the members occurs in 2 motifs. The most common one is this bicycle 330 dioxybicyclooctanone, these 3 examples here. And the group of these that present the greatest challenge for synthesis are the ones that have an isomeric dioxybicyclooctanone, but in this case it's configured in this bicycle 321 variety. Now, these compounds exhibit some quite a bit of biological activity. It's that, as I'll show in a second, that really got us into that, but I won't talk about our work in that area. Only one had been synthesized, and that was Shaman K. This was really the low-lying fruit. The lactone's really simple here, so you might imagine that's the first one to be made. Well, the challenge here is linking these 2 chiral fragments, forming that bond that joins the quaternary carbon to the 6-carbon highly oxidized lactone. So here I just point that. I think in general, one of the still challenging things to do in stereocontrolled synthesis is to join chiral rings at stereocenters. And I would assert that it's particularly demanding when one of those attached carbons is quaternary. So that's what got us back into this problem, and it was really stimulated by these structures here. I'll get back to them in a second. Well, this joining chiral rings and forming a quaternary carbon is a challenging endeavor, and I think the older members of the audience would remember one case where this was really paramount, and that was in the synthesis of azadiractin that was accomplished in a heroic fashion by the Ley group, where the biggest challenge was making this bond that linked this left-hand fragment to this similarly, I guess, more highly oxidized unit here. And they were able to finally do this in the way that's most commonly done to link chiral rings, and that's to use some intramolecular transformation. They had to back way off, not linking here to a fully substituted or a tri-substituted carbon or even an alkene. They backed off to, they had to back off because of the challenge of incorporating that bond to a sigmatropic rearrangement of the anion here that leads to delivery, being the quaternary center attached to a very small group, an alene. Well, that's the most common way, but there are examples, one of them from our shaman K synthesis, another nice one, I think, from Kishi's work and toward the Tale porphins, that bimolecular reactions can be used to unite rings and form quaternary centers. So the two examples I have here both involve carbonyl chemistry. In the top, the Mukayama allol, or the Mukayama allol variant that was employed by Kishi. And in our case, it was the thermodynamic enolate of this cis-perhydroazulinone that was coupled with this highly reactive Michael acceptor, and we needed this extra group really not to promote reactivity, but to make the reaction irreversible because of the steric hindrance here. So I'll also point out that this is a molecule I mentioned before, which is the one spongian diterpene prepared before we had recently got involved in that area, and you'll notice here that it's one that has oxygen here, which translates very nicely to using this type of an enolate strategy. Well, this is a molecule that got us involved, and it was really from a cell biology reason. A new cell biologist at Irvine, Christine Suderlin, had discovered during her PhD that this molecule, McFarland and E, had a very unique phenotype with the Golgi in terms of fragmenting the Golgi stacks, but the fragments, rather than being dispersed throughout the cell, remain localized in the paracensular region. So this would be a tool compound to separate in cell biology studies to probe the difference between this remarkable organization of the Golgi and higher organisms in these dynamic stacks to that stack structure versus their location. So at that time, there was, I think, 200 micrograms of this left from a collection. This originates originally from John Faulkner, who, I'm delighted, isolated it initially from this nudibranch, which originally it comes from a number of marine organisms. Nudibranch feeds on it. But I'm a diver, and this is a nudibranch you see quite often in Southern California. Beautiful nudibranch, I think. Okay, so if I go back just a second here. So the issue here, in the Jeff Bodie's talk, what you'd like to do is have two fragments that you can combine. So you would form this bond. Perhaps this carbon, the challenge, in principle, going in, stereochemical challenge looked pretty simple, because this bond is formed on the cis side of the cis-perhydroazuline. We'll see that sort of surprised us initially. But the junction here is that you would have to react with one of the two diastereotopic sites on the one carbon bridge of this bicyclo 321 lactone. And I think there's no extant chemistry to do that, but a kind of thing that should challenge us for the future. Well, what we did in initially looking at this, that bicyclic lactone was known only in these natural products, so it hadn't been made. So as we tried to learn how to make this bridge bicyclic unit, we developed a strategy which we thought could allow us to couple a chiral fragment that would be facially biased with a nucleophile, in this case a model tertiary nucleophile, just T-butyl. But it's that chiral matching of the two fragments that leads to control of this bond, as I'd indicated in several slides, in a bond that joins two fragments. So the strategy here was to do a 1,4 addition, trap the enolate as a silyl ether, and then control really the relative configuration of this fragment with respect to the lactone, that issue that I mentioned before, by the nucleophile coming in from the side of the cyclopentanone opposite the side chain. Then we cut the double bond and then reform this around where I have the two stars there. You eventually arrive at a tetrahydrofuran ring. This is at the aldehyde oxidation state. Aldehyde alcohol, a simple cyclization here. And the last strategic step, an important one in making these compounds, is to do a Baeyer-Villiger reaction at the end to lead to what's a pretty labile structure. You know, this is a tetrahydrofuran with two pretty good leaving groups, both stereoelectronically very nicely designed to leave in axial positions. Well, so this was our early efforts in the area. And then the strategic options with that chemistry in hand, then these are two that we considered. The first would be to do something very similar to what we use in Shaman K, to take a thermodynamic enolate, condense it with some fragment. Interestingly, we didn't start doing that, although we completed the synthesis first that way. So this enolate does react with complete stereoselectivity from the convex face with the electrophiles at this type. I think this is halogen in the case that we do. But a disadvantage of this strategy is that these molecules, apomorphine and McFarlane and E, in contrast to Shaman K, are not oxidized in the cyclopentane ring of the hydroazolene. So you'd have to remove that. It can be done, but that was not such an attractive proposition. And a much more interesting proposition was to break this bond retrosynthetically into two fragments, this, and one of them being a fairly complex tertiary organometallic. And I think and you could imagine many different things here for the metal. I think 4 or 5 years ago when we first started this, cuprate was perhaps the most obvious. And what was really interesting at that point, and what really stimulated us to pursue this, is that there really, I think we do not use tertiary organometallic reagents in complex molecule synthesis. As far as I know, there are no structurally complex tertiary trialkyl organic intermediates that have stereogenic CM bonds that have ever been employed in synthesis. So this was an interesting prospect. Perhaps some of the concerns is how you're going to make this, and you know, we know a tertiary organometallic is pretty reactive. You could imagine many side reactions. Okay, so how do we form these? If you're aiming for a cuprate, you're thinking of a lithium or Grignard as a precursor, likely. In a complex setting, reductive lithiation would be an attractive approach, but as I'll point out in a second, in highly complex systems, you're usually not going to have access to tertiary halides. They're likely not going to be stable, not so easy to make. So we looked at the other reductive lithiations that we could do, and we were really stimulated and inspired by work of my colleague, Scott Wignowski, who's in the audience, who was the first person to generate a trialkyl tertiary organolithium. He trapped it intramolecularly in cyclization reactions being developed in his lab. More stable ones that were benzylic had been trapped bimolecularly. But not surprisingly, we found you could generate those with this one-electron reducing agent, LIDBB. But these lithium reagents are voraciously reactive. and I think are of just moderate utility in synthesis. To trap them with an aldehyde, you have to add it really quickly, and you can get the product. But I think what is generally useful, and one of our more important observations in this area, was that transmetallation of a trialkyl tertiary organolithium to a cuprate occurs extremely rapidly at -78, just within seconds. And a variety of copper transmetallating reagents can be used. And these tertiary cuprate reagents are stable. I think these are reagents that could have a reasonably broad utility. So here are some initial, I guess, sort of model studies for the synthesis we had in mind with adding some fairly simple tertiary cuprates to this type of a cyclopentanone. Okay, so to pursue the synthesis, what we needed was the precursor then of the lithium reagent in this hydroazoline, the cis-perhydroazoline family. And Martin Schneerman, a very talented postdoc in my lab, designed and implemented very quickly a very practical way to make gram quantities of this, starting with inexpensive fenchone. It's been known for over 100 years that you can cleave this bond by a Beckmann fragmentation to lead to structures that have a cyclopentene with an allylic quaternary carbon with the fragments. Here you can imagine this carbon is this one. And then the key reaction in building this is a pretty standard one, I think, in making cis-perhydroazolines, and that's to do some type of intermolecular cycloaddition, in this case a nitrile oxide dipolar cycloaddition. So that leads readily here. We had some challenge in that this cyano-ketone that we got from the product of unraveling the cycloadduct, both kinetically and thermodynamically deprotonates at this site, undoubtedly because of the strong inductive effect of the nitrile. But we finally took advantage of that and implemented chemistry that my colleague Chris van der Waal had developed to make sesquiterpenes with exomethylines, and we're able to use cross-coupling to introduce the TMS methyl fragment and then allylically rearrange that to make this. So we had access to gram quantities of that during this project. And within real delighted one afternoon when Martin does this reaction that a lot of us have been waiting for, combines these two. That time we used two equivalents of this. The yield was really good, 70% of the union of these. A single product was formed in high selectivity, but the excitement waned very quickly when one started to do NOE analysis and stereochemical analysis on the product. And really, to our complete surprise, still surprises me to this day, that this union occurs not from the convex face, the less hindered face, but from the concave face with very high selectivity. So you're forming this new bond on the inside of this cis-fused bicyclic. Well, we spent some time looking at what the origin of this. This is understood to a certain level, but not in great depth. We know this isn't just a property of the cuprate. The lithium reagent does the same thing, the organolithium. I should point out that people are not familiar with this chemistry, that this LIDBB, reductive decyanation, proceeds via a tertiary radical, so the configuration of the nitrile is unimportant. The radical is then reduced to lithium reagent, and then that's trapped with CO2 to give also predominantly the product from reaction in the more hindered phase. And we thought the double bond was the issue. That was a ligand on lithium, but if you remove it, you still see largely this concave selectivity. Since these are really, to my knowledge, the first of these chiral trialkyl organolithium reagents that had been prepared, the basic mechanistic understanding of whether they react with SE2 retention or inversion isn't really known. Perhaps protonation here suggests that the lithium reagent is on the concave face. Protonation usually occurs with retention. collaborated with this in this area. The lithium reagent is computationally more stable in this series when it is on the concave face, not the convex face. And I won't describe that anymore here, but if you're interested in that, look at our discussion in this paper. Well, one thing we took from this, and it's really good that this happened, because it seemed clear, irrespective of what the origin of this was, undoubtedly the problem was that the nucleophile has this counterion, copper, and it must be that the organometallic that's leading to this unusual selectivity. So one way to get away from that is to remove the metal and look at another family of tertiary nucleophiles, and that would be tertiary radicals. So carbon tertiary radicals are, of course, highly nucleophilic radicals. We'd thought about doing this for a long time, but we would probably never have looked at this if that reaction had had occurred in the other sense of stereoselection. But we turned to look at this, and really most of the rest of my talk will focus on what we've learned about what I think is a remarkable utility of tertiary radicals in synthesis. Okay, so if you imagine us in our lab, we had the nitrile here. You can hydrolyze that nitrile with some difficulty, but you can hydrolyze it to an acid, and then you think of generating the radical by some type of decarboxylation. And it's, I think most of us would be aware of what I would say the first renaissance of radical chemistry, free radical chemistry, in small molecule synthesis back in the 70s and 80s, where Derek Barton and Bernd Giese were the real pioneers. Barton had introduced a method that we still use today to generate radicals from carboxylic acids, making these thiopyridone oxy esters, and that's one really good solution. Now, if you practice that chemistry, you know this is really useful. I think it's extraordinarily important chemistry, but it is a real pain in the whatever you want to describe. Barton esters, they're not very stable. You can't chromatograph them. They're light sensitive. And Martin Schneerman then became aware of a paper that Dave McMillan highlighted right at the end of his talk, that it isn't just in the last few years that visible light photoredox catalysis has been studied by organic chemists. And this remarkable paper, I think, of Seiji Okawa in 1991, he developed the use of N-acyloxythaliimids as radical precursors. And the beauty of this is really twofold. One is you don't have to deal with an unstable Barton ester. Thalamid is usually a very nice functional group to make things crystalline. In fact, if you add thalamid to this acid, this really greasy acid, that intermediate is in fact crystalline. So we turned to look at this. So here is, I think one theme of this conference is the importance of visible light photoredox catalysis. But this is the one example of tertiary that was reported by Okada at a mantle, pretty atypical tertiary, but decent yields. And this is a fairly complex cycle that you need an external reductant to reduce photoexcited Ru-BP to Ru-BP1, and then that can transfer an electron, perhaps synchronously with fragmentation of the NO bond. This may not be an intermediate at all. To eject that to lead to the carboxy radical. These decarboxylate almost at a diffusion control rate to give the tertiary radical, which then is trapped. Now, if you use a dihydropyridine in this as the reductant to do the reductive quenching step in this catalytic cycle, you also develop eventually, after deprotonation of that product, also a very strong vinylogous alpha amino radical. Those are also good electron donors. So there undoubtedly is a chain component of this that also proceeds by electron transfer from that radical. Well, after some tinkering, we implemented a version of this chemistry which, rather than used the biennial equivalent and did this in THF water, we moved to dichloromethane, used a Hansch ester, and using a very simple setup with low intensity visible light, either these LED strips or just compact fluorescent light. These couple very well. The yield, in fact, for forming that bond is really quite good. And in fact, the yield for forming that bond is really superb, because you isolate 62% of what you want, and there's about 15% of the product where you've lost chlorine. And that would be completely expected by anyone that is conversant in this photoredox area, because Corey Stevenson's very first paper, one of the people that's helped reinterest our community in this chemistry, was in fact doing dechlorination of alpha haloketones. But the major product is the one containing chlorine. We need the chlorine because, remember, we have to have a double bond here to clip this open to recyclize. And under conditions that are not so unattractive for fragment coupling, just using a slight excess of the, this is the major product, and importantly now in the radical coupling, the bond is formed as expected from the convex face. So this cut off a number of steps in our first synthesis. The synthesis now is, I think, 18 or 19 steps. It could be made shorter, but I'm not sure there's a need for that. It turns out that, as I didn't mention earlier, these small model compounds that we made earlier, where rather than the cis-perhydroazoline, we just have a T-butyl group, they show the same phenotype in the Golgi, and they're less toxic, and they're really the more important tool compounds. Well, what we observed in this total synthesis program really then focused the research in my lab in the last 2 or 3 years, really looking at these questions. How general is fragment coupling with these sterically bulky reagents? I think neither of these classes of reagents had been used in demanding contexts. And then a second question was, how general would this stereochemical complementarity be that we solve different stereochemistry with the cuprate or the radical? So here's another example in the cis-perhydropentylene series. We see the same thing. Radical coupling occurs completely from the less hindered face, while the cuprate reacts with a real preference, 4-to-1 preference from the more hindered face. Well, the radical chemistry, I think, is the more important, and that's mainly what I'll talk about from now on. Okay, so we've been looking at this in several different areas. I mentioned when I introduced this family of natural products that many of them have, rather than this bridge bicyclic lactone, have this cis 330, the fused bicyclic lactone. And you can certainly imagine constructing that in perhaps a much easier way, or what turns out to be an easier way, using a similar strategy, coupling a tertiary radical with some type of a butenolide. If a radical would add to not a very good radical acceptor, this tri-substituted butenolide, but if it would, there would be pretty quick entry to those. And also for our cell biology studies, we needed probe molecules in this series. And you could imagine adding a bunch of linkers this way. Okay, here are 2 examples of this chemistry. It's just in the methyl cyclohexyl series under really ideal conditions, I think, for fragment coupling, equal amounts of these. The Hansch ester as the added reductant, also Hunix base. Pretty good yields here for coupling to join a quaternary carbon to a secondary carbon. Diastereomer selectivity with respect to the methoxy group is really exquisite, as it's 10-to-1 all trans to having the epimer here. Yield a little better without that side chain, and of course 1 isomer. And what's attractive here is that these products in really a one-step no isolation sequence can be converted to the cis-bicyclic lactone. One way to do that is to doubly reduce to reduce here, cyclize to lactone, and then that is reduced. And then, of course, the intermediate here is one that you should be able to oxidize without adding an oxidant other than acetone, and doing an Oppenhauer oxidation. And that can be done. That's my favorite way of doing it. That's, I think, not quite as clean as using silver. My coworkers prefer to do this. But irrespective, these products readily are transformed to these. And so here are some examples. There are many more. Kyle Schenthal has one of the posters here, either tonight or tomorrow night. Here are some examples here, using, again, fragment coupling, using 1-to-1. Here are two natural product-derived carboxylic acid, here a drug-derived carboxylic acid, and couplings in, I think, useful yields for forming this sp3 tertiary secondary coupling and conversion to the lactone. And in fact, this is the methyl derivative of the chilivitaline A, one of the spongian diterpenes of that family. Okay, some of the other molecules that we were contemplating addressing in the lab are shown here. I outlined the tertiary radical intermediate to U1, and thinking about this, it was pretty clear that what you'd really like to have as a precursor is a tertiary alcohol. And I think in general, that's going to be a general class, a very attractive precursor. So we turned our attention to that, and as in much free radical chemistry, we stand in the shoulders of Derek Barton, because Barton had developed a way to implement his thiopyridone chemistry with alcohols as well as carboxylic acids by having an oxaloyl spacer, by employing an oxaloyl spacer. So a tertiary alcohol condensed with oxaloyl chloride. This is a pretty labile intermediate, but it can react with the N-hydroxythiopyridone. And then the Barton free radical chemistry then fragments, you lose 2 equivalents of CO2 to generate the tertiary radical. And this is really excellent, I think pretty widely used chemistry still today to do reductive deoxygenations at tertiary alcohols. It hadn't been used effectively in forming carbon-carbon bonds, but I think that is very likely maybe just from not being enormous attention paid to that. This is the best example I'm aware of, the one I show here. Well, what we decided to do was certainly not rocket science, but was just to really combine Okada and Barton and take advantage of this, the nice properties of these N-acyloxythioimides. So the procedure that was finally developed by Greg Lackner and Kyle Kwasdorf, Greg was recognized for this chemistry by the poster award I was pleased to see on Monday. What you do, you take N-hydroxythiamide, XX of oxaloyl chloride, pump off the excess to lead to the half-acid chloride, and that under conditions that we've optimized pretty carefully, these condense with a wide variety of tertiary alcohols to lead to the tertiary alkyl N-thaliamidal oxalate. I'll call this an APO. So, for example, you take esterone, add methyl, that tertiary alcohol leads to this product. And these yields are typically good. Now, these intermediates, I think if one looked at that, one recognizes an active ester here. So these are things you don't have exposed to water very long. You don't chromatograph on silica gel. But we found that typically, I think largely because of this thaliamide fragment, these are typically solids, sometimes they're crystalline, and we don't purify these, we just isolate these by solvent extractions and then take them on into the next step. So here are some of the examples. There are many, many more in this more recent paper, full paper describing this chemistry. But if you take these non-purified APOs, blue LEDs, catalytic amount of Rubippi, Honchester, room temperature. Typically, reactions are done in 2 hours, although this depends very much on scale. And the transformation of the tertiary alcohol to a new quaternary carbon occurs in quite high yield. This is one of my favorite ones where you take in the esterone series the tertiary alcohol to a new quaternary center. In fact, here you're establishing a quaternary center that's contiguous to another one, a typically challenging construction. There's certainly limits on this. If you substitute the beta carbon, 5-membered ring alpha beta, or 5-membered ring enones are best. Butenolides are a little better than enones, and methoxy group here, presumably by inductive lowering of the LUMO here, is even better. So the yields are, I think, quite good here. In this case, because these APOs are fairly labile, we use a slight excess. Yields about 15 to 20% less if you did this 1-to-1. But I think typically pretty good yields here. Now, one of the limitations here, and I won't describe it in this talk, but in this double decarboxylation, the decarboxylation of a carboxy radical, as I pointed out, occurs almost at the diffusion-controlled limit, but about 10 to the 6th slower is the decarboxylation of an alkoxy acyl radical. And if you have something tethered, if you have a competing fast other reaction, that can be a problem. Now, I want to also point out that I think we're now in an era where it seems to me this is like the second emergence of great interest in radical chemistry. We've seen this in quite a few talks in the conference, certainly mixing free radical chemistry with nickel catalysis, for example, and the talk this morning and the talk on Monday. Dave, the Macmillan group, will return to this, developed a very complementary way to form radicals, carbon radicals, including tertiary ones by photoredox decarboxylation of acids. And very beautiful work from Phil Barron generating tertiary radicals and some other class of radicals, but probably most importantly tertiary from different type of metal hydride catalytic chemistry with alkenes. Okay, so what I wanted to discuss here very quickly and then at the end of the talk is our recent efforts in a pretty simple class of natural products, but one that was chosen really to allow us to look at some of the characteristics of the chemistry I'm talking about, and that are transclaradanes, and I have 4 representative examples here. The claridane family of diterpenoids is a really big one. There are way over 1,000 claridane diterpenes. The trans ones that have the decalin with a trans ring fusion are one of the larger groups. And they're characterized in most of their members by this type of a structure, that you have a side chain emanating from a quaternary carbon that's 1,3 related to an angular methyl at this site. Particularly PL3, there's quite a bit of biology reported for that. We have not been able to verify some of that, so I'm not sure how significant that is. But more important, even though these are fairly simple, particularly on the left side of this, or even this, not very complex targets, there really is no efficient solution to make these. Many of the syntheses are more than 20 steps to make compounds such as PL3. Well, the chemistry I've described today, I think, allows you to disconnect molecules like this in a new way, really, and that's to disconnect the side chain into 2 fragments. And we chose this area really to ask that question again in terms of stereochemical complementarity of an organometallic and a radical. So it would be a cuprate and a radical, and the ideal acceptor for adding this 6-carbon side chain would be this 4-vinyl butenolide, which in fact is commercially available. It's pretty pricey, but you can make it very simply. So the question, how efficient would this be? And of course, would the stereoselectivity be the same with the radical and the organometallic? Now, this was going to be a really big challenge because one of these substituents is going to end up axial disposed to that angular methyl. So, okay, so let's go on. We implemented really a modern version of a strategy to make the basic ring systems that the late Ed Pears developed. Here we're exploiting some of the chemistry that I highlight in the Nature review from the Hoveda lab, that doing this very nice hydroillumination step first to make the vinyl aluminum reagent, and then importantly, the catalytic and anti-selective 1,4 addition to the beta substituted beta methyl cyclohexenone with this carbene ligand with the silver precursor that the Hoveda group has introduced. The yield can be pretty good here. The EE is, it's not great, but it's acceptable, I think. And the one thing I would notice is that we observe, because this ligand is something you have to make, you can't buy, that you can markedly lower the catalyst concentration. We've lowered it about 20 times over what Amir had reported. So get down to really attractive catalyst loading. Okay, so then pretty standard intermolecular alkylation. The ketone is converted to you introduce a methyl, convert the ketone to a nitrile. And now we had the first hint of really how hindered these molecules are, or how hindered the group is that is cis to the angular methyl, because we could never hydrolyze that nitrile. Either acid or base, brutal conditions, using catalysis of a number of different types, we could never do that. We resorted to the most disgusting way to hydrolyze that nitrile I can think about, which is to reduce it and then oxidize it. You can go to the aldehyde and then oxidize it. One of the sort of dirty secrets sometimes in initial total syntheses, we'll address that in a moment. But that allowed us to make the Okada precursor in this series. And then in a more direct way, this is in an anti-selective synthesis. In a racemic synthesis, we were able to take the tertiary alcohol you readily get from the alpha methyl version of that ketone and convert it to the thiophenyl group. And that will be used to generate the cuprate. Okay, so here is the key step. Form the cuprate in the way we described before, now with thiophenolate being the leaving group. 1,6 addition of cuprates to dienes is well precedented, so was not surprised that this works quite well. You get a mixture of double bond isomers. You can equilibrate those all to the butenolide with DBU. And importantly, the diester selectivity is exquisite. It's 20 to 1. And in fact, the new bond is not formed from the more hindered side. It's formed from the less hindered side to form solidago-lactone. Now, the reaction of one of the family that's really impressed me the most are the radical couplings here. As far as I know, there aren't any synthetically useful radical additions to dienes of Michael-type dienes. But we found that the addition to this 4-vinyl butenolide works extremely well. Yields 74%, again, selectivity, complete bond formation from the equatorial face, and you can isomerize the double bond in. Turns out the isomerization was more efficient after we put on the side chain, but to have a direct comparison here, if you do the same radical coupling with this, with the isomer here with the double bond internally, you also get the, again, this configuration at the new quaternary center. Okay, so what is going on here, as we see, as I indicated, equatorial coupling with both with both nucleophiles. So what we'd observed earlier was certainly real. In certain cases, there is going to be a complementarity between the cuprate and the radical, but obviously that's not going to be the case all the time. Okay, this intermediate silicagolactone can be used to make a number of transcleridane diterpenes. I mentioned two here. The precursor is silicagolactone. This is also a transcleridane diterpene. When we tried to isomerize the double bond in, we initiated a backbone rearrangement, so that allows you to make halobane diterpenes. This is a halobane diterpenoid. Okay, so this results in a reasonably decent synthesis of transclaridanes. The earlier ones, this one is 9 steps from things you can buy. But what I want to end with in my talk here is to point out one of the limitations of this Okada, the oxalate version of the Okada chemistry, and then one way that has been solved. Okay, so here again is the synthesis I described earlier of that ketone. You introduce the methyl, you get to this tertiary alcohol. And from the beginning, we didn't really want to have to take that ketone and make the nitrile to make the acid. We wanted to use these APO intermediates to generate the tertiary radical. But in this case, undoubtedly reflecting the steric hindrance of this tertiary alcohol, we could never make these intermediates. And I think the conditions that allow you to acylate that tertiary alcohol often involve conversion to the conjugate base were too severe that this product didn't survive. But what you can do is that you can, in good yield, deprotonate the tertiary alcohol and condense it with a chloromethyl oxalate to form the the mixed oxalate intermediate. And since one end is tertiary and the other methyl, you can readily hydrolyze at the methyl end. So in nearly a quantitative yield, you can isolate the cesium oxalate. And now using really Dave's chemistry, this results in a collaboration. Dave's group and my group decided to collaborate in developing this variant of the tertiary alcohol chemistry. But now taking the cesium oxalate, the coupling now with the more expensive but really required more highly oxidizing iridium catalyst, the yield is really pristine. This has been run, I think, twice on scales of 100 milligrams or more, and the yield is at least 95%. So yeah, that's, I think, one of the to me, one of the things that really stimulates us to work more in this area. Okay, so this now solution is I think, a pretty attractive solution to make transclaridanes. This is a transclaridane diterpene, and this is now made largely as a single isomer now in 6 steps from things you can buy. Okay, for those of you, some of this, the results of this collaboration between Dave's group and my group is described in a poster that was Chris Jamieson and Yuri Slutsky presented on Sunday. But if you didn't see this, here are a few examples. I think there are about 75 that'll be that are in this manuscript that we're going to submit. And I think in most cases, this is going to be a preferred way to do this, to convert a tertiary alcohol to a new quaternary carbon. A lot of the same scope we see with the phthalate. In a few cases, this is not as good. But in terms of green chemistry and atom, this is remarkable in that the only byproduct in this chemistry are 2 moles of CO2 in the Macmillan chemistry. The price you pay is that the photocatalyst is much, much more expensive than rubipi, but I think in many cases this will be preferred. Okay, so that's the story I wanted to tell today. And I wanted to conclude with just with a few observations. One is one I want to make in sort of a passionate way, and that is I think natural product total synthesis still remains a fertile area for really understanding and inventing new chemistry. I hope in my lecture it was clear that a number of the things that we've gotten involved in were stimulated by us worrying about how to make a particular natural product. The insight in chemistry was much more important than the natural product itself. I indicate some of those things here. And unfortunately, we're currently in a period where there is, I think, a lack of respect for people that tackle complex structures, such as the gorgeous work that Mohammed described yesterday. Well, certainly another thing that the last part of my talk, I think, taught us is that structurally elaborate tertiary cuprates and tertiary carbon radicals are useful intermediates for fragment coupling and making quaternary carbons. And I think the bimolecular actions of tertiary radicals are really exciting. And I thought I'd just give a scorecard here that sp3 coupling using tertiary radicals has now been demonstrated. In my lecture, I demonstrated it with tertiary primary, tertiary secondary with these simple trialkyl tertiary radicals. And last night we saw beautiful examples of tertiary coupling with these more persistent benzylic tertiary radicals that Movasaki described. So I'm anticipating in the next 10 years that there's going to be rapid development in coupling sp3 carbons, some of it from what was indicated earlier today, in merging the radical chemistry with metal chemistry, some just further exploring different coupling partners for tertiary radicals. But that's chemistry, I think, that we'll see a lot of developments in. Okay, why I don't do any of this, as I think all of you know. These are the people that have contributed to what I talked about today. Chris Beaudry, now at Associate Professor at Oregon State, got us started. Martin Schneermann, who's now down the road running his own lab at the NCI, was a major player in much of the chemistry we've done. Here are the people that, number of the people that are with me now that I mentioned that have been key in working in this area. I acknowledge them with their names here, as I did during the talk. And in this area, I've collaborated with a number of people. Ken, as I mentioned, in trying to understand the reactivity of these tertiary organometallics. Christine Suderlin and Jen Prescher in looking at the Golgi, the more cell biology area. This is a postdoc of Ken's, and most recently with Dave. These people have been funding me. So what I wanted to close on was just to remind everyone that the award that I received tonight is really recognizing the work that's been done in my lab for over 40 years. I've been fortunate to have more than 300 really remarkable coworkers, and it's really their efforts that allow me to stand here today. So I will say for anyone, the young people in the audience, if you're considering an academic career, there can't be anything more wonderful than working with young people, watching what they do. I mean, on Monday, I stand there with a former graduate student of mine in complete amazement of what he's able to do, but many, many others. And it's just so much fun to watch the development of young scientists that we mentor. So let me conclude there. We could discuss that more over beer, but thanks again.
We have time for some questions, just a couple of questions.
I see why everyone's squinting up here.
So if you have a question, wait till you get the microphone, and the microphone will, as soon as you start talking, the microphone will go on.
I see why people stood over.
Bob Beckman, University of Rochester. It struck me that some of the radicals, particularly in the last Claridane bit, have other possible chemistry that could go on with them beside what you want. And you're obviously combining two radicals that have to persist for some time to find one another.
No, we're
the
not
question
combining
is,
two radicals.
Do you see any fragmentation chemistry?
No, the chemistry I described is addition of the radical to the to an alkene, not radical-radical recombination. So, I mean, radical-radical recombination requires persistent radicals, and that was, key to the
But you
to the
could
work
still
that Mojave
imagine
described.
transannular fragmentation chemistry that could lead to an allylic radical, at least one case.
Sure,
Yeah, and you don't see any of that.
we don't see that. Bob, if you're suggesting that it's really remarkable how high these yields can be, I agree with you. I mean, I think that's why this chemistry looks like it ought to be looked at more.
Is there anything known about the biosynthesis of the azulene-based natural products? It seems unusual that half of it is highly oxygenated and half of it is not. So is the bond-forming reaction the same one that you're making?
No, it's sort of alluded to on a slide. I could go back to it, but spongian is a skeleton, a pentacyclic skeleton that's made by typical squalene terpenoid biosynthetic route. And it's believed that that's cleaved, that leads to a carbonium ion in the A and B ring. It's that carbonium ion that can rearrange to have Wagner-Riverine rearrangements to give you hydrazolines or decalins, and then the top fragment, which in a spongian diterpene, has a furan unit, then is further oxidized. So, I mean, that's the speculation. I don't think there's anything known at the enzyme level on the biosynthesis of these.
Any other questions? Please join me in congratulating Larry and thanking him for a great talk.